yeah, this video is also recorded and will be made available to you. Yeah, today we talk about classification methods, and in order to integrate these classification methods into the whole picture, or to position classification methods within machine learning, first of all, my question: what are three main components of machine learning? Very good. So this must, this is one of my goals, to brainwash you in this course, that you can answer this question in the middle of the night. So first component, data. Second component, hypothesis space. Third component, loss function. And classification methods is a subset of machine learning methods that considers particular choices for data or features and labels of data, for hypothesis spaces, and for loss functions. And we will talk about this subclass or some particular examples of this subset of machine learning methods, which are known as classification methods today. So first, let's look at data in classification methods. As I told you, data in the most general sense is nothing but a set of atomic units of information. This is a highly abstract concept which gives you a lot of flexibility. So you can basically model, I would say, anything as data points. However, you must make it clear, you must define it for your application. You must give a precise characterization of data points. And data points are characterized by two types of properties. The first type of property are features. This is everything that you can measure easily from a technological point of view, but there are also other aspects. Yesterday we heard about privacy aspects. So some features might be easy to determine technologically. You can look up the name of a person easily from some register, but there are legal constraints that, for example, allow only policemen to look up personal data, and not everybody. But in this course, we say features are properties that can be measured easily, at least technologically, from a technology point of view. But then there's another type of property, which we call labels. The label is any higher level fact or quantity of interest. And you can define what the label is. So let's look at a particular classification problem, which has been proposed by one of the students as a bonus task, and which I would like to take up here in this lecture. This classification problem is to find the best position for a basketball player. So a data point is here a basketball player. We have many basketball players, and a particular basketball player is characterized by the features like the height, the weight, then some statistics on scoring, on rebound, and so on and so forth. And the quantity of interest that we would like to know is what is the optimal position where we should use this basketball player. And for example, for this particular basketball player, the optimal position is shooting guard. And in classification, we have only a finite number of different label values. So does anybody know basketball? How many different positions are there in basketball? 5? Do I hear some other guess? 11? Somebody else? 3, 6, 7? So I'm not a basketball expert, but I found in the internet these positions. So I don't know how true that is, but at least according to this web page that I used, there are 10 different positions. So the label, which is the optimal position of the basketball player, or where the basketball player should play, can take on 1 out of 10 different values. So one value is point guard, another possible label value is shooting guard, another possible label value is small forward, and so on and so forth. So the classification problem now is, how can I tell the best position a player should play based on his or her features? And in contrast to to regression problems, which we talked about on Monday in our previous lecture, we don't have a distance measure, or there's no obvious distance measure that allows us to compare different label values. So let's say I have another classification problem. For example, I want to find out what object is on an image. And then you have an image for which somebody decided the true label is fish, because the fish is the center of the scene that we see in the image. But we use one classifier which reads in the image and makes the prediction dog. So the first classifier comes to the conclusion that a dog is on the picture. Another classifier comes to the conclusion that the human is on the picture. So which classifier is better here? There is no distance measure. Like in prediction, where we had numeric labels, we could say that a prediction 11 is closer to the true label 10 than a prediction 100. But here we don't have it. So this makes us thinking about other loss functions than in prediction or regression problems. So for the sake of exposition, I will now focus on binary classification problems. So this is the the simplest non-trivial case of a classification problem, where we want to predict only a label which can take on only two different values. So there's one question: can there be multiple labels, like a picture is labeled as dog and as fish? Yes. So a generalization is multi-label problems, where we do not want to find only one label, but we would like to find, let's say the label would be a list of 3 objects that are most likely on the image. So you can extend this basic concept of discrete labels to very complicated label values. But in the end, also when you have multiple labels, you just have a more complicated set of finite different label values. So the label values would then be combinations of dog, human, or fish. But in the end, it's a finite number of label values. And this is what characterizes classification problems: a finite number or a discrete set of label values. Then was another comment: when labeling, is it always the case that labels must be predefined? Yes. So you define what the possible label values are. And again, the important point is you define what the possible label values are. Nobody tells you, there is no mathematical theory that tells you in general what is the right choice of label values. It's the business case or the customer that gives a constraint what the possible label values are. For example, another example is claim processing, insurance claims. So an insurance claim comes in and you want to classify it into 2 categories or 2 possible classes. The first class is those insurance claims which are a bit fishy. So they may be fraudulent, and you might forward an insurance claim which belongs to this class to a human expert, which looks more carefully into this insurance claim if there is a risk of fraud. And then there's another class, which means most likely not fraudulent, and this insurance claim goes forward to a fast track where you don't screen more carefully. So here the label values are defined by the application. You have an insurance company, and as an insurance company, you are interested in finding the frauds. Yeah, and for convenience, in what follows, I use the label values +1 and -1. And this is just notational convenience. It helps me to make formulas look nicer. But there is no real meaning in using +1 and -1. We could also use 0 and 1 as the 2 label values, or a rectangle or a square and a star as 2 label values. So you just need 2 different objects to represent 2 different label values, but it turns out to be just convenient to use +1 and -1. Okay, so now we are finished with the first component, data. The second component is hypothesis space. So in classification problems, the predictor function, which reads in the features, outputs, in the end, outputs only a finite number of different values. So if you plot the function or a predictor map, then it looks like this. It has only a finite number of values. So we call a predictor map for a classification problem also classifier. But mathematically, a classifier is basically like a predictor. It's a map that reads in the features, like all the statistics of characteristics of a basketball player, and produces an estimate or a guess for the label, like the optimal position. And machine learning or classification methods, as a subset of machine learning methods, are then methods that learn or find a classifier which best matches the true labels. So how, in this basketball application, where do we get data points for which we know the true labels? Does anybody have an idea? So we need data points for which we know the true labels in order to find a good predictor map. So where could we get labeled data points? So the basketball players for which we know what the right position was. Yes, historic data, exactly. We look at the most recent seasons of basketball of NBA and looked how well did, for example, this player, I guess this is Michael Jordan, how well did he do on the position shooting guard? And if he did well, then we know this was the right label value. Yeah, and what might be a bit confusing at first sight, but makes very much sense when you start using classification methods, is that we allow classifiers to be real valued. So we typically construct classifiers not like shown here, that they take on only the label values like +1 or -1, but we construct classifier maps that can be real valued, any real number. And at first sight, this seems a bit stupid because the label value is only +1 or -1. So why should I then use as a classifier a map some real number? However, it turns out to be extremely useful to do this. First of all, we can always obtain a classification by thresholding. So we can say, I compute the classifier map and it gives a positive number, then I say, okay, this label seems to be +1 or -1 if the predictor of the classifier map is smaller or equal than 0. So I can always get the classification by thresholding out of this real number. What is more, if I use a real number, I can also use the absolute value, and we will use this absolute value to represent the confidence or the trust in the classification. And this is very important. We often want machine learning methods not only to give us a prediction, but also a measure of confidence, or how much do we trust this prediction. Humans like such measures. The customers want such measures. So there was one comment, if we have no historic data, can we use experts to assign the right labels? Yes, exactly. So one big class of, or one broad, let's say, approach to get labeled data is looking at historic data, looking at how well did the basketball player in last year. Another big idea to, or a large class of methods to get labeled data is to use experts. So to have NBA stars, previous NBA stars, like, I don't know, who are NBA stars, Karl Malone, Michael Jordan. These are experts, and they look at a young basketball player and provide the label. They say this guy or this girl needs to play at that position. So experts can provide labels, yes. Then there's another comment, in binary classification, is the sum of the prediction always 0? No, we don't compute the sum of these label values, even though we use real numbers, +1 and -1, to represent two label values, we should not use them too much as numbers. They are just two different objects, a +1 and a -1. And we should not do too much computation with the final labels themselves. Okay, so yeah, let me now continue. I will then address these questions later, but let me now continue with the classifier. So we can get a classification by thresholding the classifier, and we can use the absolute value as a confidence measure or trust in the classification. So, and it's sometimes useful to represent the classifier map by looking at the feature, at all possible feature values. So let's say we have two features. The x1 is the horizontal axis, and x2 is the vertical axis. And a particular point in this space corresponds to two numbers, the first feature and the second feature. And then a classifier divides the space into two components. So the first component is all the data points with features resulting in a classifier value larger than 0. And the other component is all the data points with features such that the classifier map is smaller or equal than 0. So it's sometimes useful to visualize a classifier by looking at these decision regions, because they could tell you, when it comes to detecting fraudulent claims, in this area, there are a lot of fraudulent claims, and this area has some meaning regarding features. So this first feature here is large. So the first feature might be relevant for the fraudulent detection. Okay, so what kind of classifier maps could we use? So how many possible classifier maps are there that take two features, two real valued features or numeric features, and output some number? How many such functions do you know? Or how many are there? Infinite. Again, yes, infinite, and very much infinite, uncountably infinite. So we need to restrict to a subset of functions, which we call a hypothesis space. There are different choices for the hypothesis space. A particular machine learning method corresponds to a particular choice for the hypothesis space. And again, the first candidate for such a subset of predictors, for such a hypothesis space, is the set of all linear functions. And you might remember that we heard about linear functions already last lecture on regression methods. And indeed, we use the same hypothesis space. We can use the same hypothesis space as we used for linear regression, we're now using for classifiers. So we use the set of linear functions to output a value, a classifier value that allows us to, first of all, get the classification by comparing this value with 0. So if this value is larger than 0, we say the label is +1. We estimate the label as +1. If this value is smaller or equal than 0, we estimate the label with -1. Yeah, so we use the sign of this classifier to get an estimate for the label, +1 or -1. But we can also, and we will also, use the magnitude of this function as a reliability measure. So let me illustrate this here. So let's say we have some features and we compute this linear predictor, which is just a weighted sum of all the features. So this expression here means first weight times first feature plus second weight times second feature, and so on and so forth. So this is a weighted sum of the features. And if this weighted sum is larger than 0, we output the label +1. If it's smaller or equal than 0, we output -1. But we also get the confidence measure. So if this value is very large, very positive, then this means we are very confident in the that the label is +1. On the other hand, if it's very much negative, this function value, then we are very confident that the label is -1. And if this value is around 0, then we are not very confident. There's a low confidence. So if you base a decision on such a classifier result, for example, the decision might be by the Prime Minister of Finland to open the schools again, then the Prime Minister would prefer to know how confident are the predictions. For example, the predictions that the COVID-19 epidemic is now going down. And if the confidence is around 0, then it might be good to wait a bit with opening the schools again. So there's one comment. Do you mean that the closer to 1, the more confident we are? So it's unbounded. So this value can be as positive as possible. So it can be 10 to the power of 8. So there is no, it doesn't stop here at 1. It can be as large as possible. Another comment. So if the classifier value is 100, we have more confidence in the label than if the value is 0.1. Yes, exactly. So the politician, for example, the Prime Minister would be very happy to get a prediction from the machine learning advisory board of the government, which has confidence 10 to the power of 8. So they are very confident. Yeah. Okay. So now we have talked about data. So we use discrete values or labels which have only a finite number of values. We have talked about hypothesis space. For example, we use linear functions. Yeah, there's one component. Can it be confident but wrong? Yes, that's possible. And this is what we want to avoid the most. So we want to avoid that this classifier map for some data point outputs a very positive number, but the true label was -1. This can happen, yeah. That's an error, and that's a very bad error because the classifier was very confident that the label should be 1, but actually it was -1. And how can we avoid that we ever use such a function, that we learn such a function? How can we avoid that? What do we have at our disposal to punish such a classification? Exactly, the loss function. So we will now talk about loss functions that exactly are very large. So there's a large loss if the prediction or if the classifier map is very positive. So there's a high confidence in 1, but actually the true label was -1. And also the loss function should be very high if the prediction is very negative, so the classifier is very confident that it's -1, but the true label was +1. So in these two cases, the loss function should be large. And we will now see loss functions that achieve this. So there are loss functions that achieve this. And one way to arrive at such a loss function is to use a probabilistic model for data points. So we interpret the label of a data point as the realization of a random variable. And we then have an interpretation of the fraction of data points with a label value +1 is nothing but the probability that the label is +1, since we now model it as a random variable. So there's one comment. If the confidence can be as high as chi, how do we know what is high confidence? That's a very good point. So how do we know absolute values? For example, 100 is high confidence. And this depends on the model that we assume for the data. So this is something we can only say what is a high confidence if you assume some probabilistic model for the data. And I will now explain you one such probabilistic model, which leads to a particular loss function. So we assume that we interpret the label of a data point as a realization of a random variable. We can do that. Nobody prevents us from that. But it must make some sense, and it makes sense because once we interpret the data as random variables, we can use statistical learning theory to guide the choice for a loss function. In particular, we can choose a loss function that is such, or that is equivalent to maximizing the probability of the data points that we observe. So once we use this probabilistic interpretation, learning a classifier map is essentially equivalent to maximizing the probability that we observe, that we actually observe the data points that we have in our training set. And I have written out in a bit more detail how this derivation works. For those of you which had some math course, this is easy math. I don't want to discuss it in detail now, and you don't need to understand this derivation within this course. So this is just a derivation that should justify that we arrive at this loss function. So for this course, it's enough that you know that this loss function exists. So it's called the logistic loss, and the logistic loss does exactly what we want. So it is very large for the case of a wrong classification. So we are very confident that the label is +1, but actually it was -1. And if we have this, think this with high confidence, then this loss function goes up, very large. On the other hand, if we have a high confidence about a correct classification, so we think that the true label is +1, and it actually is +1, and we are very confident, then the loss function is small. There's small loss involved in such a classification. So this is exactly what we would like to have. So it penalizes, it punishes, this loss function punish wrong classification, which are also made with high confidence. So you are wrong, and even so with a high confidence, you're wrong. This is very bad. Around low confidence, the loss function is some intermediate value. Okay, yeah, it's bad, but it's not too bad. What is very bad is if you're wrong and you're very confident about your wrong classification. Okay, so this is the logistic loss, and this looks very different from the squared error loss. Let me now show you how the squared error loss would look like that we used for regression problems. This would look like, oh my God, this is challenging here. So excuse my hand drawing, terrible hand drawing. This would be squared error loss. And why would this not be a good choice for classification problems or to learn a classifier? So the squared error loss would punish also wrong classifications, and it would also punish more if the wrong classification is done with high confidence. However, there's a problem. Does anybody recognize a problem when using the squared error loss? Yeah, it's symmetrical. So it also goes up. The loss becomes also large if you do a right classification with a high confidence. So this is exactly what we would like to have, but the squared error loss punishes this. That's why squared error loss is rarely used for classification problems, because it punishes correct classifications which are made with high confidence. So it's not a good idea to use the squared error loss. Yeah, and we now have arrived at a first method because we have identified data representation. So we use real numbers to represent the features of a data point. We represent labels using two different values or categories, +1 and -1. And we have identified or chosen a hypothesis space, which is the set of all linear maps, linear predictor or classifier maps. And we have chosen a loss function, the logistic loss. So we have filled all three components, and we have a machine learning method, which is called logistic regression. And I've also shown here the scikit-learn Python object, which represents logistic regression. Okay. Logistic regression is an example of a linear classifier, because if you look at the decision regions, they have a very simple shape. So a linear classifier divides the set of all data points based on their features into two half spaces. So one side of this hyperplane is the side where this linear function is positive and we classify as +1. The more we are away from this hyperplane, which is also called prediction or decision boundary, the farther away we are, the more confident we are in this classification. And on the other side, we classify as -1. So with a linear classifier, you can only implement such decision regions. However, you can use other loss functions. So this, let me put in here also the logistic loss. It looks like this somewhat. So this is the logistic loss from before. But we can also use, there are also methods which use a different loss function. One loss function is called the Hinge loss, which looks like this. Does anybody know or recognize some characteristics of this Hinge loss function that might be relevant or important? What properties does this function have, this loss function? Does this have particular characteristics that are good or bad? Yeah, so after a certain threshold, there is no punishment at all. So it goes exactly to 0. Some other properties that might be important when we want to minimize it. So maybe some of you have heard about convexity. It's a convex function, which is nice. We can easily minimize such functions, but as pointed out by one of you now, it has a corner here. It has a corner where it's not differentiable. So it's non-smooth, it's non-differentiable, which makes it more difficult to minimize compared to the logistic loss, because the logistic loss is a smooth convex function. So the logistic loss is a smooth differentiable convex function like the squared error function, so we can minimize it using gradient descent, which is nice. In contrast, the Hinge loss is also convex, but not differentiable everywhere. It has a corner. Okay, then there is another loss function that is used often, which is called the 0,1 loss. So it has only 2 values, loss 1 for wrong classification, loss 0 for correct classification. How do you like this 0,1 loss function? How do you like the shape of the 0,1 loss? Challenging, yes. It's a challenging function because it not only is non-smooth, so for example here around 0, you cannot compute the derivative, you cannot go down a gradient here, it's too steep, there is no gradient, and moreover, even more worrisome, it's non-convex. So convexity means that if you combine 2 points on the function with a straight line, all points on the straight line are above the function. So this is the case for the Hinge loss. However, if you combine this point with that point of the 0,1 loss, you have some parts of the function being below and some being above. And this is called a non-convex function. And non-convex functions are in general very difficult to minimize. So it's very challenging, computationally more expensive to find a good linear predictor that minimizes the 0,1 loss. However, you don't need to worry about this in this course because guess what? Both loss functions are implemented in Python objects. The first one, the Hinge loss. So you replacing the logistic loss with the Hinge loss yields the support vector classifier instead of logistic regression, and it's implemented using this Python object. And the 0,1 loss, replacing the logistic loss with the 0,1 loss gives the naive Bayes classifier, and it's implemented here in Python using this object. And in order to minimize or to find the predictor or classifier with the minimum loss, even though the 0,1 loss is difficult to minimize, however, in Python, it's as easy as using this object here and one method. Does anybody know the method, the name of the method that finds the predictor map with the minimum loss? Which function fits the linear predictor to the data points by minimizing the loss? Yes, fit. So dot fit, this method for this naive Bayes classifier, also for support vector machine, in this function, the predictor with minimum loss is found. So there's one question: when optimizing the 0-1 loss, is there other ways than brute force? Yes, there is. You learn more about this in more theoretic machine learning courses, or you can read about in textbooks. And the idea is to, instead of trying to minimize the 0-1 loss, to interpret minimization of 0-1 loss as a probability estimation problem. And then you can estimate probabilities by using sample averages. But this is far beyond the scope of this course. But there are clever ways to minimize the 0-1 loss. Okay. Yeah, so far we only talked about linear classifiers, which per se can only classify data points by dividing them into two half spaces. So there's one comment: is this a design choice? Again, I mean choosing the loss function. Yes, exactly. Exactly. The loss function, which loss function you use, is up to you. It's a design choice. For some loss functions, there are useful Python implementations like these objects. But you can implement your own machine learning method using your own loss function, but then you cannot use these objects. Then you need to use some optimization method yourself. Okay, so far we only talked about linear classifiers, which divide data points into two half spaces. So if the features of the data point are on this side, you classify as +1. If the features of the data point are on that side, you classify -1. But for some applications, the data doesn't look like this. It's nonlinear. The data points are nonlinear. But still, you can use linear classifiers, but you just need to use new features, because also the features that you use is a design choice, and you can construct new features as you wish. And you could construct, for example, if you want to classify data points according to highly nonlinear decision regions, so you want to categorize all data points in this region, calligraphic C3, into category hard. You want to categorize all data points that fall into this region as category cloud, and so on and so forth. And you can use a linear classifier like logistic regression for this. You just have to use new or construct new features. And you can construct features just by saying, if the features, the original features, so let's say we have two numeric features of a data point. I'm sorry, it was a domestic issue. So if you have two features, C1 and C2, you construct new features by saying, okay, the feature xj is 1 if the raw features are in the corresponding region. So you have one new feature for each region that you would like to use for classification. And then once you have these new features, you just formulate a linear classifier using these new features. And this idea of expanding the scope of linear predictors or linear maps by using new features, this is also underlying a class of methods known as kernel methods. Maybe some of you have heard about kernel support vector classifiers. And these are nothing but support vector classifiers like we talk about here, like this here, a linear classifier, but you use the support vector classifier for new features. And these new features are constructed using kernels. But we don't discuss more about kernel methods in this course. Okay, so Yeah, we have heard about logistic regression as one particular classifier. It's a bit strange that a classifier is called logistic regression, but it's based on the fact that we use predictor functions to not only get classification results like +1 or -1, but also confidence values for the classification. Yeah, and we have heard about other linear classifiers which use different loss functions, like support vector classifiers which use the Hinge loss, and naive Bayes classifier which uses the 0-1 loss. And these loss functions have different characteristics in regarding their statistical and computational properties. As I pointed out, for example, the 0-1 loss is non-convex, so it's more difficult, more computationally challenging. However, it has some statistical properties. For example, if you minimize the 0-1 loss, you can show that you minimize some error probability. So from a statistical point of view, minimizing the 0-1 loss is optimal under a certain probabilistic model. However, this comes at the price of more computation required to minimize the 0-1 loss. In contrast, the logistic loss is nice, is differentiable and convex, so we can minimize it using relatively little computational resources. Okay, that's all for my point about classification methods. Are there any questions? So there's a question, what would be the difference between clustering and classification methods? Very good point. So clustering and classification are highly related methods. The only difference is in clustering, we do not have one single labeled data point. So clustering is basically doing classification without having any labeled data point. Yeah, and we will have a whole round on clustering, which is round 5. I will talk about the relation between classification and clustering there in a bit more detail. So then there's another comment. We talked about binary classification. How does this expand to multiple classes? That's a good question. So you can reduce any multi-class problem. Like let's say we have a multi-class problem of classifying an image into fish, dog, and human. And then a standard strategy is called one versus all, one versus the rest. So the idea is to break down a multi-label problem or a multi-class problem into several binary classification problems. And the idea is quite simple and is as follows. So instead of classifying into fish, dog, or human, you do first, you classify, is the picture showing a fish or something else, like dog or human? Then you do another binary classification problem, which tests, is the picture showing a dog or something else, like fish or human? Then you do a third binary classification problem that tests, does the image show a human or something else? And then for each of these binary classification results, you get a confidence, you get some confidence measure, for example, using the absolute value of the linear predictor. And let's say you get a confidence that the image is human 90%, you get confidence that the image is dog 10%, and you get confidence that the image is fish 5%. And then you take the classification result with the highest confidence. So that's the basic idea of this one versus rest or one versus all multi-class classification. It's essentially reducing this problem to a set of binary classification problem. And you have one binary classification problem for each possible label value. So this binary classification problem for fish tests, is the image fish or not? Then a binary classification problem, is the image dog or not? And so on and so forth. Then there's another question. What's the difference between a classifier map and a prediction function? It's the same. So I use the term classifier map and prediction function interchangeably. It's a function from features to either to label space directly or to some real number, which is then thresholded to get the classification label and a confidence value. But in the end, both classifier maps and predictor functions are just maps from the features to some label or to some real number that gives the confidence in a certain label value. Then another comment, so is clustering an unsupervised method? Yes, we call a method unsupervised if it does not need any label data. Okay. Are there any other questions? Okay, thanks a lot. And I will notify you about the lectures next week by tomorrow. Thanks a lot and have a nice evening.